Have you ever stopped to think about the invisible cost of your everyday AI prompts? I mean, every single time we ask a chatbot a question, generate an image, or just get a smart reply on our phones, there are massive amounts of computations happening right behind the scenes. But, what's the actual energy price tag for all that convenience? Well, let's dive into this explainer, because uncovering the true energy cost behind AI is absolutely fascinating and, honestly, a little shocking. We're going to look at this staggeringly high energy footprint, but more importantly, we're exploring the brilliant, cutting-edge ways engineers are actually slashing that power draw by 50% or more. To really appreciate the solution, we kind of have to grasp the macro problem first. Right now, cloud data centers consume an estimated 1 to 2% of our total global electricity. And yeah, that figure's only going up. To put that into perspective, just training a single large-scale language model, like GPT-3, burned through roughly 1,287 megawatt-hours. That is literally the equivalent of the annual energy usage of 120 US households. Just let that sink in for a second. The massive computational power required to make these models smart is creating a very real environmental toll. So here's our roadmap for today. We'll start with the AI energy crisis, then look at halving the power footprint, shrinking AI models, the shift to edge AI, and finally, a sustainable hybrid future.
Okay, part 1. The AI energy crisis and the massive scale of cloud computing.
When we talk about big data and machine learning in the cloud, we're really looking at this massive bottleneck of energy consumption. It's not just the AI thinking, right? It's the data storage, the complex network transmission over super long distances, and the incredibly heavy model training phases. All these layers stack up, demanding continuous power. And what's wild is what happens during the inference phase. That's when the AI is actually generating responses for users. Take a massive 65 billion parameter model, like Llama, for example. When engineers scale up the batch sizes of requests and spread the work across more GPU shards to get faster throughput, the energy consumption in watts just spikes. We're talking exponential increases in power draw just to handle more requests faster.
Moving on to Section 2, halving the power footprint through hardware and algorithmic efficiencies.
So how do we actually stop this exponential drain? Well, engineers aren't just sitting by. They're fundamentally redesigning both the physical hardware and the core mathematical algorithms to stop this waste in its tracks. And here's our first massive victory. Simply by changing the math, developers can achieve up to a 50% reduction in training energy. It works like this. By switching a model's arithmetic from single precision, which is known as FP32, down to half precision, or FP16, the AI uses significantly less memory and processing power to calculate its neural weights. It's kind of like realizing you don't need to calculate your grocery bill out to 10 decimal places when 2 will do just fine, right? It's this brilliant optimization that literally halves the energy required for billions of calculations, all while keeping the model's accuracy pretty much exactly the same. But the 50% savings don't stop at the math. When we zoom out to the data centers themselves, integrating renewable energy, like solar and wind, with AI-driven demand forecasting slashes carbon emissions by another 50%. Basically, these intelligent algorithms predict exactly when energy demand will peak and then route the workloads to use available green power globally. It's literally AI managing its own energy footprint to maximize sustainability. How cool is that?
Section 3. Shrinking the AI models. We're making AI smaller and smarter.
To save even more energy, especially on our personal devices, we absolutely have to make these massive AI brains much, much smaller without losing their smarts. The first trick for compressing them into tighter spaces is called knowledge distillation. Think of it like a brilliant professor passing down only their most critical, condensed notes to a student. Instead of the student, which is the smaller model, having to read the entire library from scratch, it just learns the exact patterns and conclusions the massive teacher model already figured out. This lets a tiny model perform almost as well as the giant one, drastically dropping its energy consumption.
Next up, we have pruning. If distillation is passing down the notes, pruning is aggressively taking a bread pen to them and just editing out all the fluff. You see, neural networks often have connections, or neurons, that don't actually contribute much to the final answer. By strategically removing these redundant parameters, we streamline the model structure. It becomes leaner, faster, and way less power hungry.
Now, let's see what happens when we put these together into a distill then prune pipeline. First, we distill the teacher model to retain only the essential info. Then, we prune it to eliminate the physical redundancies. Studies from our sources show that combining these steps cuts the model's inference energy consumption by up to 40%. You're getting nearly the exact same performance but burning drastically fewer watts.
And the final piece of this miniaturization puzzle is quantization. This involves converting the network's weights from high-precision formats, like 32-bit floats, down to lower precision formats, like 8-bit integers. Think of it like taking a massive, ultra-high-resolution raw photo and compressing it into a JPEG so it actually fits on your phone. It drastically reduces the model's memory footprint and computation cost. Suddenly, this huge model that used to require a massive cloud server fits comfortably right in your pocket.
Which brings us to Section 4, the shift to Edge AI. Moving processing from the cloud to your pocket.
We are actively moving processing away from those power-hungry, centralized cloud data centers and bringing it right to you. In this architecture, there are generally 3 layers: the device layer, right at the bottom, the edge layer in the middle, and the cloud layer way at the top. By offloading computation to the edge, meaning running the AI directly on your smartphone, your smartwatch, or a local network gateway, we save massive amounts of energy. Why? Well, because we completely eliminate the need to continuously transmit raw data back and forth over cellular networks to a distant cloud. Processing locally can reduce data transmission by over 80%, which translates directly to incredible battery and energy savings.
When we compare these locations, on-device, edge server, and cloud, the trade-offs are actually super clear. On-device processing gives you the absolute lowest latency. I mean, it's instantaneous because there's zero network delay. It also gives you the highest privacy, since your data never leaves your phone. Now, while the compute power is definitely more limited than the cloud, it requires absolutely zero network dependency. You could literally be on a flight in airplane mode, completely offline, and your AI still works perfectly. Finally, Section 5, a sustainable hybrid future and balancing power and efficiency. So, does all this mean the cloud is dead? Not at all. The reality is that the future isn't exclusively on-device or exclusively in the cloud. It's a highly efficient, carefully orchestrated hybrid of all these systems working together. The whole trick is how we balance it. A hybrid architecture routes high-frequency, routine, or really private tasks straight to your local device. But when you ask for complex reasoning or broad knowledge retrieval, it securely routes that heavy lift up to the cloud. Combine this with dynamic voltage and frequency scaling, which, by the way, dynamically adjusts hardware power on the fly, along with split computing networks, and AI dynamic scheduling can save an additional 15 to 33% in energy. We literally use the heavy power only exactly when and where we need it.
Because artificial intelligence, machine learning, and deep learning are so deeply nested within one another, their power demands just compound as the tech gets more advanced. But by layering all these optimizations across the board, from those 50% math savings down to pruning, all the way to edge computing, we can actually sustain this rapid technological growth without totally overwhelming our power grids.
Which leaves us with one final thought. What is the invisible energy cost of your next AI prompt? While the energy footprint of AI is vast and definitely growing, the incredible 50% savings we've explored today across math, infrastructure, and edge computing prove that a sustainable future is entirely possible. So the next time your phone auto-completes a sentence instantly, just remember the incredible energy-saving science happening right there in your pocket. Thanks for joining me on this explainer, and keep questioning the technology around you.